everybody, from your favorite artist, electronist here. What I did here, actually, this is a project that took me longer than I wanted, and uh, for the driver of the motors, for some stepper motors, and it's a complicated subject, but one of the ideas that I wanted to achieve, and I did it myself without any kind of help from anyone. And I am right now, at the moment, I am upset on some people because, yeah, doesn't matter. Uh, but the idea is that I really wanted a stepper angle rotation. So this is the circuit that is really doing it. I spent some good hours on it and a good sleep, and then I come back after I refreshed after sleep with a clear mind, and it paid dividends. It paid well in the sense that I resolved the problem. I had a ton of errors, a ton of errors, and you will see in this circuit is not really as a normal circuit because I had to adapt to this very needy program. The Proteus program is needy. It doesn't like is special. It's very special. He doesn't like certain ways of doing things like in reality, but it does. You have to learn its errors pretty much, and you have to learn what he likes and what he doesn't like, which it put me a ton of errors. The biggest error and the biggest problem that I have with this simulator is the three-state option. A three-state is when, let me actually exemplify. As you can see here, do you see this gray? Let me actually point it to you here. This gray square there, that means that is not positive nor negative. So this is, where are you? This is positive on this end of the switch. So this is staying high to 5 volts or whatever. And this blue square is negative and is representing the minus negative. But this gray is neither positive nor negative. So this is very, very important because this is actually is a it is in reality like that, or they kind of try to emulate to simulate the reality, but in reality there are, and I know that there are some surges through the components, like microamps and micro voltages, and they kind of want to simulate this but it's messing up of the bigger picture. It's messing up the component itself. It's a shit, song. It's a shit song, and they. I had to reinvent the wheel to find a way, pretty much, and I find a way. So these are some notes here. This electromagnet that I have here, or a relay, it's actually a relay, and this is also a relay, also a relay here, and here as well. So on, I have three relay. Let me point better with this. So where are you? Command select. Okay, this is one relay, two relay, three relay, and fourth. I think this is it. They actually, in reality, they should be transistors. So imagine these relays are actually transistors, but in this simulator, if I put there a transistor, it will not have that three-state. Let me show you again. This three-state form, like I'm having here. Okay, these are problems that I overcome them actually, and I don't know. I tried a lot of permutations here until I get these results that I want. Here I have a very clever tweak, if you want. 4017, I forget decade counter. Decade is numbering like 1, 2, 3, 4, 5 until 10, 0 to 9, which is 10. And reset, master reset, MR here it means master reset on whatever pin you want to reset, and then switch, not to let it count to maximum. Let it count to whatever you want. This is very important thing here. This is the most the most. This is how much I could minimize the entire circuit, pretty much, and I hope you can observe and be amazed. A resistor to ground. That's it. This is the minimalization, the maximum minimalization of this entire circuit that we have here. So back to the real thing, actually, to show you how everything is. Also here I have a buffer instead of a transistor. Because again is doing that three-stating, as you can see, that is in reality, but here in the simulator doesn't want to do it properly with the transistor actually. On the transistor we have a binary transistor, is either positive or negative, which is not really the case. In reality we have three states there. We don't always, when you switch it off, is going to negative. Is not correct, is not true. Is going to a no indecisive state, a three-state mode. In air, the pin is in air if I disconnect it from the base. But if I want to put that specific pin to the ground, I put a pull down resistor like I did here. You see, if I put this dude there and I link it to ground, and yes, that pin is to the ground and is switching between two states, high and low, but not by itself. That's the problem. That's one of the problems, many problems. But let's not talk too much about the problems. I did wanted to emphasize, and I did wanted to to make you pay attention when you are working with this program. You have to overcome a lot of problems with it. You have to keep in mind there are a ton of problems, and everyone is dealing with them. Not only me or you if you work with this program. So let's actually run it. One second, one second. Let me tell you about some specification of this circuit because it's important. I put it on initially I put it on 10 hertz, and now it's on 16 hertz to count a little bit faster, not to wait for it. The stepper motor also is very important to have its specification that I modified. When you create a new motor here in Proteus, it will make it at 12 volts, but I change it to 5 volts, and it will give it a default value of 90 degrees per step, but I change it as 5.625, as you can see there. And the rest are the default values. I don't care about them. For this simulation is working very good. 5 degrees is enough to see it rotating it. If I change it to 1 degrees, it's very hard to see it rotating. Actually, we can see it right now. You see from 5 to 5 degrees, and reset and play it again because the switch is on the other side of the circuit. Okay, so let's play it. We will see this counter that is doing its job actually. When you first play the simulation, I always have some problems with counting a little bit higher or lower than it should be. But after I reset it, it is counting to what I designed it to be. So that's another kinky bullshit, another error you have to face. You have to understand about this program. You have to deal with it. So every time I'm resetting this counter here, it is counting to 16 and is stopping. Actually, this is the relay. Let me here with the bigger. You see, this is the relay that is actually stopping after the counter is reaching 16. This is the counter actually here. That's the brain. This is just a visual aid to help me in the first place count, and not really count with my mind, but see it's there, see it in reality. So now this is a very clever, like I said, device or chip or implementation, better said. But you see here is the red square here. You see it here? That means it switch on this line. But if I'm pressing the button from the top there, it will switch to the second line and then to the third line. And then when it's reaching this one, it will go back very quickly to the first one and commutating it. So pretty much this is what it's doing. And this is its button. I put it there because it's easier inside this circuit. So you see when I'm pressing that button, is switching 1, 2, 3, and then 1, 2, 3, and it is. I put a big LED, red LED for each. Let me actually show it like this. This is one counter. Actually, it's saying they're counting to 16. Let me redraw that like this. And this is counting to 2. You can see it here in the name, and here, and here, and here. This is another module. These are 3 modules I built so far. I can build 10 to fill up all these 10 pins actually, but I didn't really need. I only need a demonstration of the maximum that is possible, and the maximum, the margins, the maximum and minimum of this circuit. The first, yeah, kind of is the maximum. You will get it in a second. So now let's see. Yeah. I said that I put a big red LED to designate which module is activated, because it's very hard to see that little guy there. And when I'm switching from this switch, is commuting to 1, then 2 to 3, and then coming back to 1. And all right. So now it's back to 1. And let's reset the counter actually. And it's doing funny business because it's the first run. This is not happening in reality. I hope not. Only on this simulator, the first when you play it the first time is just erroneous. But after the second and the rest of the switches is just fine. It's normally. There is some trick somewhere. I don't know where is that trick, but to actually make it count correctly from the first try. But yeah. All right. So this is actually, you can see the motor there. So let me do this to actually show it. So pay attention on the motor how it's spinning when I'm pressing. Here, that is actually doing. Let me actually do it. Reset the entire program. So that counted to 17. Yeah. So this is like 1/4 of the rotation. 1/4, like 90 degrees. Yes. But I didn't sync this stepping angle rotation from the angle point of view, because that I will actually measure in reality with a compass, and I will with a degree angle device, and I will step through all the counts. And I will count until I will reach my desired angle, and then that will be the decisive angle that I wanted. Doesn't matter how many counts it will have. But here I'm lucky to have this 16 as 90 degrees. Here it's counting to 2. Let me switch it first to this module here, and then resetting. You see the first time is counting only 1, but it's bullshit, or that counter is not really, I don't know. But the other ones are performing as normal. Also pay attention here, this is very interesting actually. Where are you? Here in this area, where are these LEDs? And you will see only this one and only this one will flip all the time. And also pay attention to the motor itself. You will see how I will make many permutations for you to see. Let me center it like that. So when I'm switching, you see, back, 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 and back. But the degrees are not actually 2 degrees. These are steps that this made from the counters. In reality, I don't know. Actually, this is a longer discussion. But let me finish presentation to present what I started already, not to jump to the other. Next one is the last one, which is counting to 48. These are extremes, if you want. So this is the extreme maximum that this counter, binary counter 74LS93, can count. It can count only for until 16, and then is resetting itself to 0. Right. And this is the minimum it can. The same counter can count to only to 2. And this is also so that's the maximum. This is the maximum, and this is the minimum. But this is another maximum, a composition of 2 counters to count over the limit of itself. So it's using 2 counters to count over it to whatever number I want, pretty much, and which is you'll see the effect in a second. So it is switch to this module here, and let's reset it to when I'm resetting it. Shit, is resetting to this guy here module there. I'm switching to this module here, and now when I'm pressing, pay attention to the motor how. So it's like 3 by 4 times. It's not 4 by 4, but 3 by 4 times. It's now it's straight. I cannot zoom because correctly because this program is not letting me zoom correctly. So what it's doing? Let me use arrows. So right now is here. Then it will go here, and stop here. I think. And yep, let's do it. Let's see if it's doing it as I told you. Yes. And next, 1, 2, 3. Yeah. Okay. So so next it will be 1, 2, 3, and it will stop here. And next it will be 1, 2, 3, and it will stop here, and so on. 1 horizontal, 1 vertical, and let's here. So this is. Let me find a centering. Wait. Yeah, this is good enough. So you see. And it is actually counting to 48. You can see it here on the counter, and it is turning to a specific angle and stopping there. And that's very important because this is exactly what I wanted from a stepper motor. And let's see. Yeah, about stepper angles, because this is another subject. Let's get here, and I want to discuss it. In MI8, I have these 3 steppers, known brand steppers. I have no unknown brands as well, scrapped from printers or whatever. But these are brand new brands, and very commercial, you know. And this guy, let's see. No, I don't have the pictures with. No, we have to see here. So you see, it says stride angle, but it's not really stride angle. You couldn't put their step angle. It's that hard, and it's not 5 degrees, 5.65 degrees over 64. It's yeah, it's kind of this guy, but it's really yeah, it's not really correct like that. It's not easy to understand, at least. How I write it here is straight bullseye, straightforward. So that's a circle is having 360 degrees, which this motor is turning from 0 to its back to its 0 to 360 degrees, and it's creating is having a 5 degrees for 1 step. This is how we calculate the steps. Is having 64 tooths inside the motor. I'm not sure exactly how to get this tooth number, but if you can count those tooths, it should specify here in the datasheet, but is specified very stupidly, and really not helpful at all, not user friendly. You know, it's kind of specified there, and I had to figure out what all this stuff means. I'm not that good at math. I'm an artist, you know. But this what I want to say is that this datasheet is not really user friendly. It's not that good. How they are expressing those values and how they are explaining it there. Nah, it could be better, you know. It could be better. And also the NEMA 8 and 17 both have the same step angle actually. This one is very yep. Here. So where are you? So this is the step angle. Here, 1.8 degrees step angle. You see how clear and logical and easy to understand. And plus tolerance here it says plus minus 0. I believe is 10 milli or micro degrees, which is infinitesimal, but it will add up probably. It's a backlash probably. Most probably it might be a backlash, that tolerance there. But this 1.8 degrees here in the simulator is very hard to see. Let me show you, because I did re-edited this page, this datasheet page. This is all you need really from a motor datasheet. Its voltage is amperage, although because it's using coils, it is current. driving mechanism or device. So what really matters is this amperage. But these are the safe values. You can actually drive it higher than this, but it will warm up and potentially destroy it. You can actually make a trick. You can rise up the voltage, but lower the amperage. If you don't have this kind of power source, you can power it on, let's say, 5 volts, but lower amperage, 5 volts with 1 amp, or 12 volts with 500 milliamps, probably. But you have to really stop the amperage at that level, at 500 milliamps or 1 amp. I didn't calculate it. I'm saying it that it will decrease. What value you have to calculate it yourself. But the problem is the power source. The power source should be rated and also resist that amperage, not to blow up itself. The power source must resist, and also should be the exact value of the. That's the problem, you know. So it's a power source problem, amperage problem, and voltage is changeable, and also it will change the amperage while you are changing the voltage. And to bring the motor in the silver lining way of working, you know, not too slow, not too hard driving the motor. So that's the angle step that I wanted to show you. And I think I finalized. So pretty much what this thing will do in reality, the motor will, let me actually open back that image and to paint over it, because so from one button I will switch which angle I want to uh, uh, to, to to turn this motor. So times 1 angle degree times 10, let's say, and times 45, you know, whatever. I will decide later. These buttons, what should they do? But this is what this motor will do. It will, if I will press this first one at 1 angle, it will do exactly 1 angle, and those counters that you've seen there, they will count as close as possible, and it will rotate this shaft. It will rotate only 1 angle. But if I will, let me reset. But if I will switch to times 10, yeah, like this, times 10 angles, like angles, degrees, it will do it like this, you know, back, in reality. And it will, and also the 45, as you can imagine, or whatever angle I desire, also hard coded, because this is a logic gate mechanism that I have here for circuit, and it is fixed. It's not that variable, but I can variate the angle of the motor this way, and it is pretty good actually. I really like it. Of course, it can be done with a microcontroller, much more simpler, but yeah, this is a subject of learning for me, at least. I'm learning about the logic gates, especially, and the logic ICs in general, because they are doing some interesting stuff, and you can combine the microcontrolling devices with the logic ICs or gates, and you can get some very funky results if you know the more you know, the better, you know. So that's the case here. What I wanted to show you more than this, or further than this, pretty much I think I covered everything. Oh, I put here a L298 without a driver, without a proper protection for the motor. This is just for simulation purpose only. So here, after this driver, I believe it is already having some protection diodes inside it, I believe. Huh? I don't remember. But if it's not having those protection, you should put actually protection diodes on these wires here. What else? What else? Also current driving. Like I said before, you have to limit the current through the motor before the gate, before the motor driver here, or after it. Doesn't matter. Usually in the datasheet that I discovered for the L298 is having another chip that it will come in the mail. I hope it will come from China, from eBay. If I remember it right, I don't remember it right. Let me check it out. Counters. Steppers. I don't remember really which one was. I think this one. I think it is. It is. Let me check it. Oh no, no, no. So this is the name of the chip. I don't have the chip, and the simulator itself doesn't really know this chip as well. So I had to simulate its internal circuit, like it's saying here, L6506. Very interesting chip, actually. Very nice chip. By the way, for the clarity, let me do this. Yeah, like this. This is the chip, actually. It's having some inputs here. So all these 4 lines are its inputs. Also a 5 volts rail to power the chip, and also for the enable here. These are actually the 5 volts for these resistors here, which are voltage dividers, and also this thing, this power resistor here. But it's shared between. Let me reset to be able to scroll between L298, which Proteus simulator does know about it. It does know about it, but about this chip doesn't know about it, and doesn't. It is not having it in its database at all. So no. Uh, uh, so yeah, this power resistors that I have here is shared between stepper driver here, L298, and this L6506 chip IC on one of its pins. Actually, on two of its pins, VoltaSense 2 and VoltaSense 1. I actually copied its naming, exactly its naming as it's having it on its datasheet on the real chip here. To be able to construct better the circuit, internal circuit here, and also if I'm referring to this circuit other times, I will know exactly what it's doing. So current driving is very important for stepper motors. This is I spent a ton of time understanding this concept because I didn't get it from one shot, and nobody actually told me as explicit as I'm telling you right now. You should pay attention to a couple of characteristics when you want to drive a stepper motor. It's not like willy-nilly, let's drive a stepper motor, and because one, you can burn the driver. You have multiple options to burn out, and I was kind of lucky so far because I was using properly a variable power supply, which is not drawn here, but in reality I use a proper variable power supply, which I highly recommend. If you don't have one, you should have, and I should have two of them because I only have one, and I got in the situations when I had to put a secondary power supply, and I had to scratch my balls. Where do I get a secondary power supply, and also variable if possible? So I don't have two of them. I only have one, but I'm thinking about it. So back to the problem: how to burn up? How easily is to screw it and to fuck it up? First of all, you can burn the driving circuit, which is this part. This is a driving circuit with the transistors that is actually driving the motor. In my earlier experiments, I actually managed to burn out even the logic. So the spikes from the motor, the spikes got through the signal wires through the logic, and I burned 1555 and one counter. Or two 555 and one counter, and a flip flop. I believe I burned a flip flop as well, and I don't remember if I burned some LEDs as well. I don't remember that. They are well protected, but this is so. What I did, I put some diodes here on these lines, and I prevented any kind of stupid mistakes. So here are the diodes now in this for each line pointing in that direction towards the input of the driving chip, or whatever you have there. If you have transistors, then another possibility to burn something is to actually burn the motor itself. Is if the power supply is too high for its specifications. If you put let's say let's go to the datasheet here. So let's go to the datasheet. So let's say we are giving it 3.6 volts. Okay, exactly how like in the book here, like in the datasheet. But you put the power supply at 4 amps, not 1.5 but 4 or 10 amps. You will smoke this motor as you don't know what has happened, because the amperage was too high. But the voltage was fine, was on the voltage there, but the amperage is too high. It will burn it out. The same is possible. The same is correct if the amperage is too low. You have the same voltage, but if the amperage is too low, the motor will not turn, or it will run very slowly and very shitty. So you don't want that either. And another way to burn up something is the power source itself. If I believe, if everything here is dragging too much power, is requesting too much power, is eating too much power in wattage. So voltage times current equal wattage. So if this wattage is higher than the power supply can give, the power supply will shit itself and die in smoke and flames. So pretty much, I think I covered everything. Too much. I covered too much. The entire discussion was about, and this entire movie that I made was about how to turn to a specific angle a stepper motor using logic ICs and not a microcontroller. I made it. I made it possible. I'm very proud of it. Okay. And pretty much this is it. Thank you very much for listening, and we will see next time. Thank you very much. Bye bye.